Hello my friends and welcome back to the You Can Do TV channel. Construction at Lakewood Villages utilizes the Renko structural building system, an engineered method based on interlocking composite structural elements. The system includes prefabricated blocks, columns, beams, joists, and decking components manufactured with tight dimensional tolerances to ensure accurate structural alignment during assembly. Each unit is positioned and mechanically interlocked to form the structural framework. Instead of conventional fasteners or concrete bonding, the connections rely on high-strength structural adhesives that chemically bond adjacent elements. This process creates a monolithic composite structure capable of distributing loads across the entire building system. The components are designed to meet structural performance requirements verified through certified laboratory testing to standards, including load resistance, physical durability, and fire performance. The resulting structure behaves as an integrated load-bearing system, transferring vertical and lateral forces through the composite framework. Because the components are lightweight yet structurally reinforced, the installation process requires minimal heavy equipment and allows rapid structural assembly. This engineered approach enables multi-story construction while maintaining precise load paths, structural stability, and compliance with modern building codes. Building a house the way children assemble Lego blocks may sound impossible, yet modern modular construction systems are turning that idea into reality. Using the GAB block, the second floor of a house can be assembled through a carefully organized sequence that combines prefabrication with precise on-site installation. Before work begins on the roof structure, the cavities within the timber framework are filled with insulation material. This step improves thermal performance while sealing the structure against heat loss. Once the insulation layer is complete, wooden formboards are installed across the upper level to create a stable base for the roof deck and the following construction stages. A crane then lifts the prefabricated gablock blocks to the second floor. Workers position each block one by one, locking them together with engineered interlocking joints. The elements fit together with remarkable precision, forming walls and structural sections without the need for traditional concrete work. The blocks function much like oversized Lego pieces, allowing the structure to rise quickly while maintaining accurate alignment. Because each component is manufactured in advance and designed for direct assembly, the building process becomes faster, cleaner, and far less dependent on heavy machinery, while still delivering strong insulation and reliable structural performance. Installing patio surfaces with the Aspire pavers offers a fast and flexible way to renovate aging outdoor spaces without removing existing concrete. Instead of demolishing a cracked patio, the lightweight pavers are placed directly over the surface using a patented grid system that ensures accurate spacing and alignment. Each grid panel measures approximately 16 by 16 inches and acts as a framework that locks the pavers into position. The individual tiles interlock across adjacent grids, creating a stable surface while remaining loose-laid rather than glued or permanently fixed. This design allows damaged pavers to be removed and replaced easily, or patterns to be rearranged in the future. Made from about 95% recycled materials, the pavers are durable, stain-resistant, and require minimal maintenance. Because they are non-porous, they do not require sealers like traditional brick or concrete pavers. During installation, standard tools such as a miter saw or jigsaw can be used to cut both grids and pavers to fit edges and corners. Trim components, including bullnose and transition pieces, complete the installation by creating smooth edges and connecting the patio surface to surrounding landscaping. The Skylum project has reached completion at 70 meters, making it the tallest, prefabricated reinforced concrete residential complex in Lithuania. Construction used factory-produced reinforced concrete structural elements that were transported to site and assembled floor by floor with tower cranes. The complex consists of two 20-story towers with more than 400 apartments, supported by underground parking built with post-tensioned concrete technology. Prefabrication allowed faster assembly, improved structural precision, and reduced weather-related delays during construction. At a construction site, slope stabilization is underway for the widening of street. After removing sections of an old railway embankment, crews install about 300 ground anchors up to 8 meters long. Reinforcement mesh and a 20-centimeter layer of shotcrete complete the system, creating a stable, permanently secured slope ready for future road expansion. In early 2020, China rapidly constructed the emergency Huotianshan Hospital in Wuhan to treat patients during the outbreak of COVID-19. More than 100 excavators and bulldozers first leveled the construction site, enabling immediate foundation preparation. Prefabricated container modules were then delivered and assembled into ward units. Steel frames formed two-story medical buildings, while over 300 modular units were connected to create treatment spaces. Engineers installed sewage treatment systems, power distribution facilities, and medical infrastructure simultaneously. Thousands of workers operated around the clock, completing structural assembly, utility integration, and medical equipment installation. The 1,000-bed emergency hospital was finished and delivered in just 10 days. The construction of Thyssen Test Tower in Rottweil showcases advanced slipform concrete technology executed by Bitschnau Slipform. The tower's reinforced concrete core was built using a continuous slipform system that allowed the formwork to climb steadily while concrete was poured without interruption. Hydraulic jacks lifted the formwork structure as workers installed reinforcement steel and embedded components. This method enabled rapid vertical construction while maintaining precise wall geometry and structural integrity. The process significantly reduced construction time and provided a uniform concrete surface for the 246-meter-tall elevator testing tower. The CBD New Capital Towers in New Administrative Capital feature advanced high-rise construction techniques. Reinforced concrete cores and high-strength structural frames support rapid vertical construction, while tower cranes, climbing formwork systems, and precision concrete placement enable efficient floor-by-floor assembly in the central business district development. The M27 Junction 10 Improvement Scheme in Hampshire represents a major highway infrastructure upgrade designed to transform the existing interchange into a fully operational all-moves junction. A key engineering operation involved the auto-rippage box-pushing method delivered by Freyssinet. This technique allowed a reinforced concrete underpass structure to be hydraulically pushed beneath the active motorway while minimizing traffic disruption. The process required the design and construction of a temporary guiding raft and pushing slab to control alignment during the slide. Engineers installed specialized components, including anchorage blocks, active and passive deviators, steel inserts, strands, I-pylon plates, grease lubrication systems, and bentonite layers to reduce friction. High-capacity hydraulic jacks were then commissioned to apply controlled force through tension strands. During the operation, the concrete box structure advanced gradually along the prepared sliding path with precise monitoring of alignment and load distribution. This controlled pushing sequence ensured structural accuracy while maintaining strict motorway closure windows and safety requirements. Concrete block manufacturing is a core industrial application supported by equipment developed by Besser Company. Modern block plants rely on high-capacity machines that combine vibration, compression, and precision mold technology to produce dense and dimensionally accurate masonry units. The equipment is engineered to maintain consistent material distribution, uniform compaction, and stable product geometry across large production volumes. Automated handling systems move pallets and freshly formed blocks through controlled curing environments where temperature and humidity conditions support proper cement hydration and strength development. Advanced control systems regulate machine cycles, vibration intensity, and material feed to ensure repeatable quality. This industrial approach allows manufacturers to efficiently produce concrete masonry units for structural walls, architectural facades, and infrastructure applications while maintaining high productivity, durability, and dimensional consistency. "3D concrete printing is redefining how buildings are designed and constructed, and the Maxi printer developed by Constructions 3D demonstrates the potential of this emerging technology." Engineered specifically for the construction sector, the Maxi printer is designed as a highly mobile system that can be transported inside a single 20-foot container. This compact logistics approach allows the complete printing solution to be delivered and deployed quickly on construction sites. Using advanced automated extrusion technology, the printer deposits layers of specially formulated concrete to create structural walls directly from a digital model. The process significantly reduces manual labor while improving precision and efficiency. Automated construction also eliminates many physically demanding tasks traditionally performed by workers, shifting the focus toward digital design, machine operation, and advanced construction planning. Environmental performance is another core element of the system. Innovative materials such as locally produced linen flax can be integrated as thermal insulation, helping reduce the environmental footprint of the building process. Since completing one of the first 3D printed buildings in France in 2019, the Maxi printer platform has already been adopted by numerous universities and research centers, supporting experimentation with new materials, architectural forms, and sustainable construction methods. By combining automation, digital modeling, and eco-friendly materials, 3D concrete printing is opening a new chapter in modern construction engineering. The BET block system uses large precast concrete blocks to create strong, flexible structures for walls, storage bays, and industrial enclosures. Designed with interlocking shapes, the blocks can be stacked quickly without mortar. Their massive weight ensures stability, while the modular design allows rapid assembly, relocation, and expansion, making them ideal for warehouses, recycling yards, agricultural facilities, and temporary construction infrastructure. The contact bin wall is an engineered solution designed to stabilize soil and support earth structures in infrastructure and construction projects. The system consists of adjoining closed-face bins, each approximately 10 feet wide, formed from durable yet lightweight steel components. These elements are bolted together directly at the job site, allowing rapid assembly with minimal specialized equipment. Once installed, the bins are filled with compacted soil or aggregate. The weight of the backfill transforms the structure into a gravity-type retaining wall, capable of resisting lateral earth pressure. Unlike rigid concrete walls, the bin wall system is designed with controlled flexibility, enabling it to accommodate minor ground movement without structural damage. This adaptable design has made the system widely used for more than 6 decades in highway embankments, bridge approaches, railways, and industrial earth retention applications worldwide. At Green Park, balcony installation becomes a fast, carefully orchestrated process. Prefabricated units produced by Sapphire Balconies arrive fully assembled, minimizing on-site work. Delivered in double-stacked configurations with lifting slings attached, the balconies can be quickly hoisted into position. Cast-in anchors connect the structure to the facade while reducing thermal bridging through integrated thermal brakes. Using the innovative glide-on cassette system, installers guide each lightweight aluminum balcony into place with precision. This efficient method allows construction teams to install up to 20 balconies per day, far faster than traditional balcony installation systems. At the Gross Reservoir Expansion Project, engineers prepare the existing structure using high-pressure hydrodemolition. Robotic nozzles deliver water jets of about 20,000 psi to remove roughly 3 inches from the 70-year-old concrete surface. This controlled roughening improves the bond between the original dam and newly placed concrete, ensuring the raised structure behaves as a single integrated mass. At the Gross Dam, engineers are raising the structure using roller compacted concrete, RCC, a method that allows large volumes of concrete to be placed rapidly in layered lifts. Concrete is produced at an on-site batch plant and transported to the dam through a conveyor system that gradually rises as the structure grows taller. Formwork installed along the crest holds fresh concrete until it cures and gains strength. The upgraded design transforms the original curved gravity dam into a thick arch structure, transferring water pressure into the canyon walls for improved structural stability and load distribution. The completion of the main dam plinth marks a critical engineering milestone in the structure's foundation system at the Chimney Hollow Reservoir. The plinth consists of a 1.5-foot-thick reinforced concrete slab running along the dam's centerline, linking the foundation, grout curtain, and embankment. Construction required drilling approximately 20-foot rock anchors into the prepared subgrade to enhance foundation stability before installing rebar cages and formwork. Nearly 10 800 cubic yards of concrete were placed along a 3 700-foot alignment that climbs the canyon slope at roughly 45 degrees. This structural element enables pressurized grout injection to seal the foundation against seepage while connecting directly to the asphalt core, forming a continuous impermeable barrier through the dam. Hybrid towers are typically used in large onshore wind farms, where hub heights exceed the limits of conventional steel towers. Production begins with the fabrication of the lower tower sections made from high-strength precast concrete segments. These curved segments are produced in specialized molds, where reinforced steel cages are installed before high-performance concrete is poured and carefully cured to achieve the required structural strength. After curing, each segment is inspected, finished, and prepared for transport to the assembly site. At the wind farm location, the concrete segments are lifted and assembled into circular rings using heavy lifting equipment. High-strength pre-stressing tendons run vertically through the tower sections and are tensioned to compress the structure, creating a rigid and stable base capable of supporting extreme wind loads. The upper portion of the tower is manufactured separately using large rolled steel shells. These steel sections are welded, surface-treated, and coated to ensure durability against weather and corrosion. During final installation, the steel tower is mounted onto the completed concrete base, forming a hybrid structure. This combination of concrete and steel allows hybrid towers to reach greater heights while maintaining structural stability, optimized material efficiency, and improved wind energy production. Modular construction can progress twice as fast as conventional building. While site operations continue, structural modules are manufactured simultaneously in the factory, enabling controlled production, higher quality standards, and significantly faster project delivery. The Titan slipform concrete paver is designed for constructing the upstream concrete face of concrete-faced rock-filled dams. The machine continuously places, spreads, and shapes fresh concrete along the dam slope using slipform technology. Its modular design allows paving widths of approximately 10, 12, or 15 meters, ensuring efficient coverage of large dam surfaces. The system delivers uniform thickness and smooth finishing, while improving placement speed and construction quality for large-scale hydropower and water storage dam projects. The concrete Lego pipe rack system, developed by Alfred Miller Contracting, uses precast components with splice sleeve connections and moment frames for rapid assembly. The modular system can be erected by a small crew, while concrete's natural corrosion and fire resistance eliminates the need for additional fireproofing and scaffolding. The modular housing project Erawet Sareci in Turkey applies off-site construction technology. Structural steel modules and precast wall panels are fabricated in factory conditions, then transported to site for rapid assembly. Precision-bolted connections, integrated utilities, and crane-assisted installation allow fast construction while maintaining consistent structural quality and dimensional accuracy. As traffic volumes continue to grow across Florida, highway noise has become a major engineering concern in urban corridors. To control sound levels near residential areas, the Florida Department of Transportation applies advanced acoustic analysis and infrastructure solutions. Engineers measure traffic noise using the A-weighted decibel scale, which reflects how the human ear perceives sound. Factors such as traffic density, vehicle speed, and the proportion of heavy trucks are carefully evaluated during roadway planning. When noise impacts exceed federal thresholds, specially designed concrete noise barriers are introduced. Typically ranging from 8 to 22 feet in height, these structures are installed within the highway right-of-way and positioned outside the safety clear zone, effectively blocking and deflecting traffic noise away from nearby homes, schools, and public spaces. In the barren region of Nouvelle-Aquitaine, a residential construction project carried out by Maison Aquitaine demonstrates the structured engineering process behind a modern single-family house. The work begins with precise site preparation and the construction of reinforced concrete foundations designed to distribute structural loads and stabilize the building on local soil conditions. Once the foundation trenches are prepared, underground service lines and insulation layers are installed. These include conduits for water supply, drainage systems, and electrical infrastructure. With these utilities positioned, contractors pour the reinforced concrete floor slab, creating a rigid base for the entire structure. Before vertical construction begins, a specialized anti-termite treatment is applied to protect the building against biological degradation common in certain regions. Masonry walls are then raised using structural blocks carefully aligned to maintain dimensional accuracy and load-bearing capacity. After the structural shell is completed, exterior finishing begins. Protective render coatings are applied to the facade, improving weather resistance and thermal performance. Window and door frames are installed next, sealing the building envelope and preparing the structure for interior work. Interior development focuses on insulation and technical systems. Thermal insulation layers are added to interior walls to improve energy efficiency. Electrical wiring and plumbing networks are then installed throughout the house, carefully routed through walls and service cavities. Partition walls are constructed to define interior rooms and functional spaces. Finally, flooring installation begins with ceramic tile placement, completing the interior surfaces. This step-by-step process ensures structural stability, energy efficiency, and long-term durability for the finished home. Two, concrete barriers play a critical role in modern infrastructure safety. Their production involves precision molds, reinforced steel cages, and high-strength concrete. Through vibration compaction and controlled curing, each barrier gains durability and structural strength, ensuring reliable protection for highways, construction zones, and industrial sites. The installation of the perfect pipe is designed to ensure both structural reliability and efficient on-site construction. Engineered for high static load capacity and corrosion resistance, the system combines reinforced concrete with an internal HDPE liner, providing long-term protection against aggressive wastewater environments. Installation begins with careful preparation of the trench and the formation of a stable gravel bedding layer. This bedding ensures uniform load distribution and allows precise adjustment of pipe level and gradient. Accurate alignment is essential for maintaining the designed flow conditions within the sewer network. Each pipe section is then lowered into the trench using lifting equipment and positioned on the prepared bedding. The connection between pipes is achieved through a precision socket joint system. The spigot end of one pipe is inserted into the bell-shaped socket of the adjacent section, forming a secure and watertight connection designed to prevent infiltration or leakage. After alignment, inspectors verify the pipe level, slope, and joint integrity. Once confirmed, backfilling begins. Selected granular material is placed around the pipe and compacted in layers to provide structural support while protecting the pipe body. This controlled installation process ensures a tight, durable pipeline system that remains easy to inspect and maintain. With strong pipe connections and reliable bedding support, the perfect pipe system enables safe construction progress while delivering long-term performance in underground sewer infrastructure. Drilled shaft foundations are widely used to support highway structures, such as lighting poles, overhead signs, traffic signal mast arms, and bridges. According to the Florida Department of Transportation, this foundation system provides high structural capacity in varied soil and coastal environments where resistance to storms and hurricanes is essential. Construction begins with specialized drilling equipment that excavates a vertical shaft into the ground. Typical drilled shafts range from 30 to 72 inches in diameter and can extend from about 12 feet for traffic signals to more than 70 feet for bridge foundations. In many roadway applications, shafts around 5 feet in diameter and approximately 30 feet deep are common. Excavated material is removed progressively while depth and soil conditions are monitored. To prevent the shaft walls from collapsing during drilling, a stabilizing slurry, usually a mixture of water with minerals or polymer resin, is pumped into the hole. After excavation reaches the required depth, a prefabricated reinforcing steel cage is lowered into the shaft. Concrete is then poured from the bottom upward, displacing the slurry. In some cases, a steel casing remains in place to provide additional structural stability. Precast pile caps deliver faster foundation construction. Manufactured off-site and transported ready for installation, they can be positioned quickly on-site with minimal labor, reducing installation time. Hitachi Zosen Innova specializes in advanced waste-to-energy and renewable infrastructure. The company designs and delivers plants that convert municipal waste into electricity and heat, combining environmental engineering, high-efficiency combustion technology, and sustainable resource recovery systems. During construction of the tri-line by Doppelmayr, one of the most critical stages is the installation of the track and haul ropes. The process begins with a helicopter flying a lightweight guide rope across the span. This guide rope is then used to pull a heavier steel cable, which ultimately allows the main track rope to be drawn into position. A 25-ton winch installed at the upper station provides the pulling force, while a braking winch at the lower station carefully controls tension. This balance prevents excessive rope sag and ensures the cable never touches the ground. Additional hit-track rope pulling machines guide the rope around bollards and maintain proper alignment. The final stage involves hand-splicing the 46mm 6-strand haul rope to create a continuous loop, ensuring strength and durability under constant tension. At an altitude of over 1,900 meters on Mont Blanc, a Liebherr 150 ECB-8 was assembled using a helicopter in a highly complex lifting operation. Due to the remote mountainous terrain, crane components were transported in multiple aerial lifts and precisely positioned on the prepared foundation. The flat-top tower crane now supports construction of a new cable car system and mountain museum, providing reliable lifting capacity for structural materials, equipment, and prefabricated elements in one of the most challenging high-altitude construction environments. Heavy lift transportation to a prepared foundation can also be performed using a traditional rolling method, where large cylindrical bars are placed beneath the load to gradually move extremely heavy structures. In operations carried out by Sinotrans Bangladesh Limited, this technique allows massive industrial components to be relocated with controlled precision even when specialized transport vehicles are not practical. The process begins with the heavy structure positioned on a reinforced sliding platform. Several solid steel rollers, thick cylindrical bars, are arranged in parallel beneath the base. As pulling force is applied using hydraulic winches or heavy-duty tractors, the load slowly rolls forward across the steel bars. Once the structure moves beyond the rear rollers, crews retrieve those bars and reposition them at the front of the path. This continuous cycle of placing rollers in front and collecting them from behind allows the load to advance steadily toward the foundation. Guide beams and alignment markers ensure the structure remains centered during movement. The rolling friction between the steel bars and support surface dramatically reduces resistance, enabling the controlled transport of extremely heavy equipment. When the load reaches the final position, hydraulic jacks gradually lift the structure so the rollers can be removed. The equipment is then carefully lowered onto its foundation supports. This method combines simple mechanical principles with careful coordination, enabling safe movement and precise placement of oversized industrial components. The perfect pipe represents an advanced solution for modern sewer infrastructure. Designed for both open trench installation and microtunneling applications, the system combines the structural strength of reinforced concrete with the corrosion resistance of high-density polyethylene. This composite design creates pipes capable of handling aggressive wastewater environments while maintaining high static load capacity and long service life. Production begins with the manufacturing of the perfect liner, the inner protective layer that shields the concrete structure from chemical corrosion. HDPE sheets are precisely trimmed to the required length according to the pipe diameter. The material is then welded to form a perfectly shaped cylindrical liner, ensuring a continuous and watertight internal surface. Once the liner is prepared, it is positioned inside the production mold where the pipe body will be formed. A thermoplastic molding joint is integrated to create the pipe socket and spigot connection system. This joint ensures a secure mechanical fit and long-term sealing performance between pipe segments during installation. The pipe shell is then produced using self-compacting concrete. This highly flowable concrete mixture fills the mold evenly without requiring extensive vibration, guaranteeing uniform density and excellent structural strength. A maintenance-free shrinking core system shapes the inner pipe geometry while allowing efficient demolding once the concrete has cured. Following casting, each pipe section undergoes careful handling through an automated transport and storage system known as TransExact. This system ensures secure and gentle movement of the heavy components throughout the production facility, reducing the risk of damage while maintaining efficient workflow. Every finished pipe is subjected to strict quality control procedures, including water tightness testing to confirm sealing reliability. The result is a durable sewage pipe system that combines corrosion resistance, high load capacity, and reliable long-term performance. Through automated production, innovative materials, and precision engineering, the perfect pipe system delivers a highly efficient solution for modern underground infrastructure networks. In spring 2016, a major track renewal program transformed a section of the historic rail corridor between Hamburg and Cuxhaven. The project focused on a 7-kilometer segment near Hornburg, where ballast cleaning, rail replacement, sleeper renewal, and full track rehabilitation were executed within a tightly scheduled 27-day construction window. Advanced railway engineering equipment ensured that the line remained operational without a complete closure. At the center of the operation was the powerful PM1000 URM. This massive machine, supported by a long train of specialized wagons, performs continuous ballast excavation and cleaning using up to 3 simultaneous digging chains. These chains remove contaminated ballast to the required depth and width, allowing reusable aggregate to be separated and returned to the track bed. By recycling large portions of the existing ballast, the system significantly reduces the need for new material transport and lowers project costs. Material logistics are handled through a coordinated container system mounted on transport wagons behind the machine. Portal cranes move containers filled with new subgrade protection material or ballast toward the machine, where the contents are discharged into onboard hoppers. Meanwhile, excavated waste material travels forward via conveyor belts to a second construction train equipped with MFS units, which transport debris to off-site disposal areas. This relay-style logistics chain keeps the construction flow uninterrupted. After the ballast cleaning phase, the RU800S takes over. This machine replaces rails and sleepers in a continuous process. Old sleepers are removed, ballast is cleaned again where necessary, and reusable material is temporarily stored before new sleepers and rails are precisely positioned. Specialized lifting and spreading mechanisms guide the new rails onto fastening points with minimal bending stress along a 45-meter working zone. Final track geometry is achieved using high-precision stabilization and tamping technology. Machines such as the Dynamic Tamping Express 094X compact ballast beneath sleepers, while a dynamic stabilizer simulates train loads to secure the track structure. Electronic pre-measurement systems ensure accurate alignment, elevation, and curvature. After 27 days of intensive work, the upgraded track section returned to service, demonstrating how modern railway maintenance technology enables large-scale infrastructure renewal with speed, precision, and minimal disruption to rail operations. In railway operations, rapid response after an accident is critical to restore traffic and minimize economic disruption. For this purpose, the advanced Kiro multitasker was developed as a powerful and highly flexible rescue solution for rail networks. Designed specifically for emergency recovery operations, the multitasker combines high lifting capacity with exceptional mobility on rail infrastructure. Traveling within a train formation at speeds up to 100 kilometers per hour, the crane can reach accident sites quickly, even in remote areas where road access is impossible. Once on site, the system can be deployed rapidly thanks to integrated counterweights mounted directly on the crane or on an adjacent wagon, significantly reducing setup time. The crane delivers impressive lifting performance with a capacity of up to 250 tons and a maximum load moment of 2 800-ton meters. Its telescopic boom allows precise lifting at large working radii, enabling damaged locomotives and railcars to be recovered safely without causing additional structural damage. This capability is especially important when wreckage lies on adjacent tracks or in confined spaces. A distinctive feature of the multitasker is its dual slewing ring system, which allows the boom to pivot independently from the rear superstructure by up to 30 degrees. This configuration keeps the counterweight aligned with the track axis, allowing work to continue without blocking neighboring rail lines. Hydraulic outriggers can be deployed individually, diagonally, or on one side only, allowing the crane to stabilize safely even in restricted spaces. Advanced leveling systems also compensate for track superelevation and uneven terrain, ensuring stable lifting conditions. Together, these engineering features make the multitasker an essential tool for rapid railway accident recovery and infrastructure restoration. Railroad spill containment is increasingly critical as freight trains transport larger volumes of liquid cargo. The UltraTrack PAN's composite model is designed to capture leaks from tanker cars, locomotives, and other rail equipment. Each 20-foot modular pan is made from durable composite materials that combine high chemical resistance with lightweight handling, allowing installation without heavy machinery. Center pans are placed directly between rails, while side pans are secured using steel rail clips and standard hand tools. Closed-cell polyethylene gaskets seal gaps beneath the rails to prevent fluid from reaching the ballast. Flow-through ports allow liquids to move between connected pans and into optional drainage systems for safe containment. Another key milestone has been completed on the KIV water supply project, with the successful insertion of 2 major water carrier pipelines through sleeve pipes at a railway crossing. The complex operation ensures safe pipeline passage beneath rail infrastructure while advancing construction of large-scale bulk water transmission system. Each low-floor tram measured about 43.5 meters in length, exceeding the capacity of standard roll trailers. Engineers developed a transport configuration using 2 coupled railed roll trailers to create an extended load platform capable of supporting the full vehicle structure. Hydraulic suspension systems ensured even load distribution during loading in transit. The trams were first positioned on specialized road trailers for delivery to the port of Bremerhaven. At the terminal, Ro-Ro loading technology allowed the vehicles to be driven onto the vessel while maintaining structural stability. This engineered logistics chain ensured safe handling of oversized rail vehicles during long-distance intercontinental transport. A heavy logistics operation was executed in the Nachten lignite mine to transport a massive excavator component used on one of the world's largest bucket wheel mining machines. Engineering logistics specialist Universal Transport deployed a self-propelled modular transporter equipped with 20 hydraulic axle lines to move the oversized structure. The steel boom element measured roughly 40 meters in length and weighed over 200 tons. The SPMT's integrated hydraulic suspension and electronic steering system enabled precise load distribution and stable maneuvering across uneven mine terrain. Operators controlled the transporter through a cable remote system while traveling a prepared 4-kilometer haul route inside the open pit mine. Upon arrival, cranes lifted the component from the modular platform and positioned it on support beams for installation. The coordinated lifting and transport operation demonstrated the precision required for maintaining ultra-large mining machinery. The HH155A hybrid tower represents an advanced structural solution developed for wind farms located in regions with relatively low wind speeds. By increasing the hub height and optimizing the tower design, this hybrid system allows turbines to capture stronger and more stable wind currents found at higher elevations, significantly improving power generation efficiency. Construction of the tower begins with the preparation of a reinforced concrete foundation capable of supporting the massive loads generated by the turbine and tower structure. Precision anchor bolts are embedded in the foundation to ensure accurate alignment for the tower installation. Once the base structure has cured and passed structural inspections, assembly of the hybrid tower begins. The lower section of the tower typically consists of large precast or cast-in-place concrete segments. These massive cylindrical sections provide exceptional stiffness and stability, while allowing greater tower height without excessive steel consumption. Each segment is carefully lifted and positioned using heavy-duty cranes, then aligned and secured to form the base structure. Above the concrete base, the upper tower is constructed using steel sections. These steel tower segments are bolted together and connected to the concrete portion through specially engineered transition pieces that distribute loads evenly between materials. Finally, the nacelle and turbine rotor components are installed at the top of the tower. By combining concrete and steel construction, the HH155A hybrid tower achieves greater height, improved structural performance, and enhanced energy production for wind farms operating in low wind environments. The Goldhofer FTV 300 blade transport device is engineered for efficient handling of large wind turbine blades. It enables crane-free loading and unloading, supports blade angles up to 60 degrees, and allows unlimited pitch adjustment. Mounted on modular trailers or self-propelled units, the system improves maneuverability on difficult wind farm access routes.